Okay, guys, we're gonna work on chapter 13 before your first test. So this is the first review before your first test, and all of these are gonna have to do with radical reactions. And so I'm gonna write a couple of notes to help you figure out each of these. And let's start. So the first one, we are doing a radical reaction here, and radical reaction mechanisms are a lot different from the regular mechanisms that we've seen in like Chem 1 and everything. So with radical reactions, I have 3 steps. Let me write those out for you. So it's initiation, which is when 2 radicals are formed. We have propagation, when a radical reacts with another radical and forms new sigma bond plus a new radical. And the last one is going to be termination. Where 2 radicals combine and this removes radicals from your solution. Removes radicals without making more. Cool. Let me change my color. And so the way that we can tell whether this is a radical reaction and not like a regular Br2 reaction is that we have a radical initiator right here. This is light. So light and peroxide, so this right here, are going to be like the giveaways that you're handling radical reactions. Okay, so then let's do the first one, initiation. When 2 radicals are formed. So I'm going to do just Br. And I'm going to break the bond between Br with half arrows. Half arrows mean that you're only moving 1 electron. And with a bond, you know that there's 2 electrons in a bond. So then I'm going to have to draw 2 half arrows. And this gives me 2 moles of Br radical. That's my initiation step. Then I have propagation. This is my first propagation. And this is when a radical reacts with, another reactant and forms a new pi bond and a new radical. There we go. In radical reactions, we take off hydrogens in order to make new radicals. There you go. So I'm going to react a radical right here with another reactant to form a new radical and a new pi bond. And with Br, there's a difference between radical bromination and radical chlorination. So with Br, we're selective for the most substituted carbon-hydrogen bond, and for Cl, non-selected. Cool. So we look at for our most stable CH bond on this carbon-hydrogen chain, and I'm going to say it's this one right here, because this one is disubstituted, whereas all of the other ones are primary. All the other carbons on this chain are primary. And this one right here doesn't have a hydrogen, so it's not like we can pluck that hydrogen off or a hydrogen off of that one. Okay. Draw my half arrows. I'm breaking a bond and making one. Radical stays on my carbon-hydrogen chain. Let me make that prettier. Sorry about that. There you go. So you just made another sigma bond between the hydrogen and the bromine, and you made another radical. So this is propagation. And so with the professors that you guys have, the ones that make you write everything out for your test, like how Doherty does, well, for Doherty, you're gonna have to write everything out. So she wants 2 propagation steps. So you show her 2 propagation steps. You can use any radical that you have formed. So this is another new radical that I have right here. So I'm going to use that one. I'm going to use a new radical. And I'm just going to do BR2. There's a lot of things that you can do. Like, okay, I always give this example. So I'll give it after so that we can look at all the things that are happening in this reaction. So I'm going to break a bond, form a new radical. I'm going to put my products down here because I didn't fit anything right. Bromine radical plus a new alkyl halide. There, you made a new sigma bond, which is this one right here, and a new radical, which is the bromine radical. So you got your 2 propagation steps, and I'm going to need 2 termination steps as well. So termination 1, getting rid of all your radicals. So all the radicals that you have in the previous reactions, you can use. So I'm going to use Br radical and another Br radical. Draw my half arrows, and I formed a new bond, Br. I'm going to do another one, a random radical that we have, which can be this right here. And I'll just do Br again. And in your products, you no longer have radicals. There you go. 2 termination steps will be good. But one thing that you do need to do is your major product. So for one of the termination steps, you do always have to form your alkyl halide. So make sure that your first termination step was the bromine with bromine. So that's good. But if you already formed the bromine and bromine, you have to make sure that your second termination is going to form your alkyl halide. This one right here. So always make sure to include that somewhere in your termination steps. Okay, so all of this looks weird. When I was learning this, I thought it looked weird because you're breaking down bromine into 2 radicals here, and then you start building it up. Like, why are we doing that? What was the purpose of all of this if we were just gonna make it again? Same thing with, let me see. This right here and this right here. So for your propagation made the same product as your termination did. Why does it do that? And so, explanation for that. When you have like a bottle of water, you have H2O, right? And it's constantly dissociating into H plus and OH minus. It's the equilibrium. They're constantly going back and forth. There's lots of things that happen at once in a solution. So same thing here. In this radical solution, there's a bunch of things happening at once. The main thing that you have to take care of is the definitions. So in initiation, 2 radicals are formed. So make sure that 2 radicals were formed and not just one right here and another sigma bond, like for propagation. So just know your terms. That's the most important part, because it all looks weird, but it's just because everything in the solution is happening at once. If things are breaking, things are making. It's very random. Cool. Next one. What are the major products for the following reactions? Difference between bromine and chlorine. Bromine is selective for the most substituted carbon-hydrogen bond, and chlorine is non-selective. So I'm going to draw the major product for bromine. And so here are all of my, what would seem would be my possibilities. So there's one right here. This one is tri-substituted carbon with a hydrogen on it. And then the next one that I see like on this type of problem, a mistake that I see often is they'll choose this carbon right here. But remember, you can, in radical reactions, the carbon-hydrogen bonds are breaking. And on this carbon, you have no carbon-hydrogen bond. There's no hydrogen on this carbon. Only methyl, or only carbon groups, R groups, there you go. So then your most substituted one would be the tertiary one that we labeled with the hydrogen. So then that's where I'm going to replace the hydrogen and put my Br. There you go. For chlorine, since chlorine is non-selective, you can draw all of the possible products that you have. So it doesn't matter if you put it on the most substituted carbon. It doesn't matter if you put it on the least substituted carbon. Everything, like, they're all going to be your products. So let me write that out. Chlorine. Hey, oh yeah, okay. Make sure that you don't drop any carbon. So for drawing chlorine, just redraw the molecule and then draw your bromine on every carbon that you have available hydrogens. I'm gonna put a plus sign over here. Remember not to drop any of your carbons. So this one looks kind of confusing, but it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Make sure that it's like that for all of them. And then I also see that people want to draw something like this. So draw the whole thing. And they want to put on another, they want to put the chlorine on another carbon like this. The thing is that on this molecule, these 3 carbons are all in similar environments. They're all on one side of the chain. They're all next to the same central atom, this carbon right here. So they're all the same carbons, basically. It's like the NMR, where you see like 9 hydrogens and a, let me see, what is that? Singlet. That would be the NMR, but notice how there are 9 hydrogens because all of these carbons are the same in the same chemical environment. So then if you draw something like this, she won't mark it wrong, but you should know like they're the same thing basically. This one and this one are the same thing. But these would be my products. These are the only ones I had to draw. If you do write another one similar to like the carbon, the alkyl halide that is underlined in blue, if you write a whole bunch of those products, she won't mark anything wrong because you did get it right. You got all of them good. Next one, match the steps with the correct term, initiation, propagation, termination, or none of these. The thing that helped me with this is drawing out the products. So you already know how to do your arrows and everything, and now you'll just connect them. So when these 2 arrows are pointing at each other, that means they're forming a bond. A tip I have for this one is number your carbons, 1, 2, 3, 4, 5. Total of 5 carbons, so I'm going to draw 1, 2, 3, 4, 5. There we go. So I'm not dropping any carbons. I'm all good. And let me number again. Look how this arrow is adding a radical to number 2. So this is going to be my new product. Okay, so then we didn't get rid of all of our radicals like in termination. So it's terminations out of the picture. Two radicals were not formed, only one was. And a radical reacts with another reactant and forms a new sigma bond with the radical. Okay, cool. That one would be it. So these two arrows right here pointing at each other are forming a new sigma bond, and this arrow right here is forming a new radical. So this is signs for propagation. Propagation. This other one, we're forming a sigma bond because these two are pointing at each other, and we're breaking a hydrogen bond and making a new radical. So then one of my products is going to look like this. That's a primary radical. And yeah. And the hydrogen is going to add on to OH to make H2O. These are my two products. So we have a totally neutral compound, so we don't have a total of two radicals, right? So it's not initiation. But we did make a new sigma bond between OH and H. So then we have a sigma bond and a radical, so this gives us signals for propagation. This next one, we are getting rid of the two radicals. None other is formed, so this is termination. Again, one thing I would get confused with on here is numbering, is dropping carbons. So make sure that you number them. 1, 2, 3, 4, 5, 6, just to know how many you have in total so you don't drop them later. So I have 1, 2, 3, 4, 5, 6. There we go. And this is termination because we got rid of all of our radicals. This one is a bit more confusing, but this is something that you have on your test. Notice how they're giving you whole-headed arrows, meaning we're not moving one electron at a time. So it's not a radical reaction at all. So then this would be none of these. There we go. Rank the radicals in order of increasing stability, 1 being the least, 3 being the most. Okay, so then some notes for this one, some notes that you need for this one. Let me bring it over here. Okay. For radical stability, this is a primary radical, and it's less stable than a secondary radical. The secondary radical is less stable than the tertiary radical. And the tertiary radical is less stable than an allylic radical. Increasing radical stability. Okay, so now we just need to figure out whether they're tertiary, primary, secondary, tertiary, or allylic. So then for my first one, this is going to be tertiary. My second one, this carbon is 1 carbon away from the double bond, so we're allylic. And my second one, we're secondary. 2 methyl groups next to it. Okay, so with our ranking system, 3 being the most stable, this will be the most stable. This will be number 2, and this will be number 1. Cool. Next one. Rank the following CH bonds from weakest to strongest. If any are the same, then state which are. 1 being the weakest, 4 being the strongest. Okay, so here are my other notes for that one. Okay. This is a primary hydrogen, and this is stronger than secondary hydrogen, which is stronger than tertiary hydrogen, which is stronger than an allylic hydrogen. So primary, secondary, tertiary, allylic. And so going towards the right, increasing carbon-hydrogen string. So the reason that the primary carbon-hydrogen bond is stronger is because it doesn't want to become a radical, like on this one over here. So carbon-hydrogen bond. If I'm already so stable, or yeah, completely stable, neutral, then why would I want something to take off my hydrogen and become a radical? When if I'm in the radical form, I'm obviously the least stable. Over here, it's easy to pluck off an allylic hydrogen because if you pluck it off, my allylic radical is very stable. So then, let's look at our answer choices. Start labeling primary, secondary, tertiary, allylic carbon-hydrogen bonds. So this one has two R groups around this carbon. This is secondary. This one has one R group, primary. This one has, okay, this one looks like it's secondary, right? But it's actually one carbon away from the double bond. So this is allylic. There you go. And this carbon has 1, 2, 3 bonds around it, so it's tertiary. And so given our notes, we can easily label these. 4 being the strongest. This will be my strongest carbon-hydrogen bond. This will be number 3. 2, and 1 being the weakest carbon-hydrogen bond. There we go. Okay, next one. Show the formation of a polymer with the following reagents. These were always more practice for me because at first I didn't understand it, but then I did a little trick for myself and that really helped. So I'll try to explain it through Zoom if I can. But let's see. I'm gonna draw my Charlie Brown sweater. That was horrible. You can draw as many as you want. You just need to at least show 3 repeating subunits. And I'll put N on the side saying that since this is a polymer, I'm just showing you a piece of the polymer, but there's so much more than outside of those parentheses. Like they keep going to the right, they keep going to the left, but I'm just showing you at one point in my polymer. Okay. This is my double bond. I'm gonna break my double bond into a V shape. So V shape. And I'm gonna break, okay, so this is my monomer. This is what a monomer is called. And so monomers are the building blocks of polymers. So with one monomer, with the alkene of one monomer, I'm gonna break it into a V shape and keep connecting those monomers to each other. So if I break this into a V shape, this will be part of it. This is into a V shape. And I still have the same substituents on it. Again, this is my double bond. You keep building up the polymers. I'm going to break it into a V shape and connect it to my other monomer. Break that double bond into a V shape. You still have the same substituents on it. Again, break it into a V shape. Add it to your representation of the polymer. I'll do one more. Break the double bond into a V shape. This will be my V and connect it to one another. There we go. These next ones are a little bit more harder. It's the same thing though. You're gonna break into a V shape. So I'm going to draw my Charlie Brown sweater first. Parentheses, boom, boom, boom. Okay. So with this double bond right here, it's arbitrary. So you're going to be able to put the fluorine group on the top or on the bottom, as long as the methyl groups and the fluorines are on opposite sides. So I'll show you right now. I'm going to break the green bond. So I'm just going to show you, this is not what's actually happening, but this is how I picture it. So it's laying down like this, and I'm going to break one like that. So on your, let me see how I can do it. Okay, this is how it is. Just look at me. Okay, so I'm going to break the double bond into a V shape. I'm going to break it like this. And notice how I have a substituent on this carbon right here and a substituent on like where my wrist is at. This will be my methyl group, and this one will be my fluorine group. So I'm going to keep attaching these subunits to one another. So let me try to do this. Break it into a V shape. And on one side, you're going to have the methyl group. And on the other, you're going to have the fluorine group. And you still have another place to attach the other ones by. So I'm going to keep doing the same thing. Break my double bond into a V shape, still have a fluorine group on that side and have a methyl group on that side. And you have another thing to connect it with, which is this carbon in that case. So I'm going to repeat. One up, one down. There you go. Break it into a V shape. One up, one down. And again, it's arbitrary. So if you choose to have your methyl groups on the bottom, make sure they're all at the bottom. If you choose to have your methyl groups on the top, make sure they're all at the top. And the fluorines are all at the bottom. And then I'm just going to do one more. Break it into a V shape, methyl group up, fluorine down. Cool. Okay, so then the next one. Charlie Brown sweater. With an N, telling you that your polymer is continuous. Break the double bond into a V and keep connecting them. So I'm going to break this one this way. Breaking it into a V, and this one stayed connected and the other side was opened. So then I'm going to keep my carboxylic acid group on one hydrogen. And just to not get confused, I'm just going to put COOH. Do another polymer. This will be my polymer. I'm keeping it closed on this side, so the carbon is closed. It represents this carbon right here. And I open the other side into a V, and notice how I still have carboxylic acid on one end. Do another one. It's repeating subunits. Keep this carbon right here closed and open the other carbon. Okay. Next ones. What monomer is needed to make the following polymers? If you basically, if you got these down, you should be pretty good. So look at how this looks like these right here. That means you're going to have a monomer similar to this. What I'm going to do is I'm going to draw my double bond and two methyl groups at the bottom. Notice how it looks similar like this, and this looks similar. They should make this monomer should make all of those, or that polymer on the right side of the arrow. And then I'm going to write AIBN at the bottom of it, because AIBN is what's going to initiate the polymerization. Polymerization. There you go. Let me see. I know there's another one that we use. Okay. Another one that we can use is BPO. So don't be confused when you see either one of those. You can use AIBN or BPO to make a polymer. So this next one, I'm going to use AIBN. This unit looks like this unit. So I'm going to have to draw a monomer similar to this one right here. Something trans. And so, I wrote it on the wrong one. Okay. On one side I have my BR, and on the other I have my fluorine. Again, it doesn't matter if you chose to put your BR down here or your fluorine down here, because it's very arbitrary. As long as you have your bromines on the top side or on the bottom side, keep them all on the bottom side, and the other substituent all on the top instead of alternating. Okay. This one right here looks a lot like this right here. So I'm going to have a monomer that looks similar to this. I'm going to draw my double bond. I'm going to act like I'm keeping this one closed. Boom, boom. And a phenyl ring is coming off. Phenyl ring. There we go. We should be good with that. That should be my monomer, and I'm going to put a BPO just to change it up. Okay. Something that you should remember for your test. For Doherty's, she again makes you write everything out. If you're given abbreviations like the pH right here, don't try to change it up. You know, that's the phenyl group, which looks like a benzene. So don't try to draw the benzene. Because sometimes you could mess up or like misinterpret what the phenol means. So just keep the abbreviation. Always keep your abbreviations. It'll be a lot easier to grade. It'll be a lot easier for you to write. Okay, last one. I'm not going to write the mechanisms because these are ones that you can just look up in the book, and mechanisms are really important. They're going to be on Doherty's test. There's going to be a page full of mechanisms, probably like 3 mechanisms, but they're worth a lot of points. What I am going to do for this one is I'm going to give you the products. And I want to have it out just to make sure I don't get anything wrong. So for HBr and ROOR, this is a radical reaction because you have a radical initiator down here. So when you see HBr with a radical initiator, you know that we're going to follow Anti-Markovnikov's rule, anti-Mark, meaning we're going to put the hydrogen, add hydrogen to most substituted carbon on double bond. So on your double bond, you have 2 possible carbons. I'm going to add the hydrogen to the most substituted carbon, which is this carbon right here. It has 2 substituents on the side of it, whereas this one right here only has 1 going up. Okay, so then if I add my hydrogen right there, then I'm going to add my bromine on the other side. There we go. That'll be my product. It doesn't have to, you don't have to like overcomplicate it or anything. Just know anti-mark, that should help you. And know what anti-mark means. Okay, cool. And again, you don't need to draw the hydrogen. I was just putting it to like implicate where I placed it. This next one, Br2 and a radical initiator. So bromine radical reactions, we know that they're very selective for the most substituted carbon-hydrogen bond. So the most substituted carbon-hydrogen bond here, or the easiest hydrogen to pluck off, basically, is going to be my allylic carbon-hydrogen bond. Let me draw all the possible ones that we have. We have this carbon-hydrogen bond, this carbon-hydrogen bond, this carbon-hydrogen bond, this carbon-hydrogen bond. We also have a carbon-hydrogen bond here, but the thing is, when you have a radical on a double bond, it's very unstable. So what did we say about carbon-hydrogen bonds? When your carbon-hydrogen bond is easy to pluck off, that's because when you pluck it off, you're going to have a stable radical. With this one, or with this hydrogen right here, if we pluck it off, we have a very unstable radical. So we really, really don't want that. So that hydrogen wasn't even a choice. So out of these four, you can pick one of them. But they're in the same chemical environment again. So this one and this one are the same, and this one and this one are the same. So you basically only have two choices. And the clear choice would be this right here because it's allylic. It's the easiest to pluck off this carbon-hydrogen bond because the radical is going to be more stable. Here we go. So then I'm just going to place my bromine right there. And that'll be your answer. So the next one. NBS, what you should know about NBS is that it provides bromine. Provides bromine to the allylic carbon. So NBS is going to be a radical initiator. NBS is going to be a radical reaction. Okay. NBS is called code for N-bromo succinimide. So since it has the bromo here, you know it's going to add Br. You can also have NIS. N-iodo succinimide. So if they try to trick you with that on the test, just know that these sound very familiar. They're just going to add different things to the allylic carbon. So this one's going to add iodine to the allylic carbon. And so one thing I know that a lot of people get confused by is, do we take off this double bond or don't? So keep that double bond and add your bromine to the allylic position. Should I drop in the carbons? That looks good. Okay, cool. We're done with the first part of our review, and I'll upload the rest by this week because I know you guys have an exam coming up. So let me see. Okay. I'll set up the next worksheets and we can do that in the next part 2 review.